Hello. In this video, I'd like to go over a worked example calculation related to two different learning objectives that we've studied previously. So continuing on with our ACE Physics review. The learning objective, solve problems concerning energy and power in electric circuits. And the learning objective to explain the effects of internal resistance on terminal potential difference and power output of a source of EMF. So two different learning objectives that we'd studied, and we need kind of both of them in order to make sense of this question. It's a good example of a question where we need to sort of combine our mastery of different learning objectives to see if we've really sort of understood it. And so I'll kind of go through this question as an opportunity to explore some of those physics concepts. The question comes from ACE Physics Syllabus Code 9702, Paper 11 from May-June 2013. Question number 32 reads, a power supply of electromotive force, EMF, 12 volts, and an internal resistance, 2.0 ohms, is connected in series with a 13 ohm resistor. What is the power dissipated in the 13 ohm resistor? Well, you can see that I've already written out three relevant equations for power as it relates to sort of electricity. So we have power equals current times voltage, power equals current squared times resistance, and power equals voltage squared over resistance. Students that sit for the ACE Physics papers should have each of these equations in mind by the time they sit for the paper. So these should already sort of be committed to memory. But this question is not just a good example of combining different learning objectives together. It's also a good example question for being able to build upon a foundation. And so being able to state or to define or to list something, that's kind of lower order thinking tasks. You know, we could memorize these equations, or we'd certainly know where to find them if we really needed them. It's not enough to just have the foundation to be able to apply it. These equations by themselves won't allow you to correctly solve this. Maybe we need sort of at least one more equation here as it relates to internal resistance. And so it's another example of not over-relying on your ability to memorize equations and then just thinking, oh, well, I'll just plug in the numbers and I know all the equations and that should get me there. Indeed, that might get you into more trouble with this question than be helpful. But indeed, you do have to know the equations here. And so let's just kind of think about each one of them. The way that I would approach this calculation is to say, well, what do I know and what's sort of the most convenient thing to calculate? I want to know what is the current in this circuit, right? There is one current that's sort of moving through this series circuit, and I want to be able to calculate it. I can kind of think about the internal resistance of this power supply as being just one other resistor in series with this resistor here. And so if I want to know the total current that's sort of being pulled from the power supply, then I could first calculate, well, what's the sort of equivalent resistance of this entire circuit? And it's just going to be two resistors in series. So how do we add resistors in series? We sum them. So there's 15 total ohms of resistance in this circuit. And then I can use Ohm's law to calculate the current over here. And so current would be V over R, where the total circuit resistance here is 13 ohms, my external resistor, plus my 2 ohms of internal resistance. Sorry for that sloppy omega class. I'll try to clean it up here. That's a better omega. So we've got a total circuit resistance of 15 ohms. That's the resistance that we need to consider when we calculate, well, how much current will sort of be in this circuit here. We know that there's 12 volts of EMF. And so we can calculate the current here, I, as 12 volts divided by 15 ohms of total circuit resistance. What's 12 divided by 15? 0.8. And so we've just calculated that the current here, 12 volts divided by 15 ohms of circuit resistance, is 0.8 0.8 amps. As soon as I knew the current in this circuit is 0.8 amps, I would use this equation because we know we're solving for the 13 ohm resistor, and so you plug in 13 ohms for resistance, plug in 0.8 amps for the intensity I of the current. Don't forget to square your value for current there, and let's see what that gives us. 0.8 squared times 13 gives us a value 8.32. Don't forget, watts are the units of power, and so choice A seems like the correct answer based on that. Some students that are, as I mentioned earlier, maybe too quick to sort of rely on their knowledge of the equations may inspect this and go, well, we've got 12 volts V, we've got 13 ohms R, and I haven't done this calculation yet, but I'm almost sure maybe if we were to plug in those values here, maybe one of these incorrect answers would be showing up in our calculator. Might capture our misunderstanding. So 12 squared divided by 13, well, that gives us 11.07. And so students that just incorrectly substitute these values into this equation, yeah, they knew the equation, but they're going to get the wrong answer to the question. They calculate it as 11 and choose D, which is not the correct answer, right? A is the correct answer here. Well, did we just prove this equation invalid or something? Well, no. We have to kind of really think about the voltage up here. You know, what do we really kind of mean by this? And how does internal resistance come into play? See how, like, in that calculation we completely neglected the fact that there's 2 ohms of internal resistance. And so remember what that really means. Internal resistance is saying we're not going to have all 12 of these volts available to this 13 ohm resistor, right? The power dissipated in the 13 ohm resistor is not going to have all 12 volts available to it. So we could kind of think about it with, you know, another equation. The terminal PD, so the potential difference sort of at the terminals of the battery, of the power supply rather, is equal to the EMF minus the lost volts, right? So we're going to lose some volts as we drive current I through this power supply with internal resistance, lowercase r. Here r is equal to the 2 ohms of internal resistance. As we drive the current through that, well, we're going to lose some volts, IR, right? So the current I times lowercase r is, you know, a quantity we typically call the lost volts. So if we've got 12 volts of EMF, but then we're drawing 0.8 amps of current from that power supply, as it's driven through the power supply here, we multiply 2 times the 0.8, and what do we get there? What's 2 times 0.8? Well, that's 1.6 volts. So we're going to lose 1.6 volts from our EMF. And so not all 12 volts is going to be available to this 13 ohm resistor, right? So we're going to have our, let's just see it all in the calculator here. We know the internal resistor is 2, and we know we've already calculated the current that's sort of being drawn from this circuit is 0.8. So 2 times 0.8 gives us our 1.6 volts of lost volts. So the terminal PD, if we wanted to use this equation here for V, then we'd first calculate the terminal PD would be 12 volts of EMF minus the 0.8 amps of current times the 2 ohms of internal resistance. And so we'd have 12 volts minus 1.6 volts. There's our 1.6 volts of that were lost. 12 minus 1.6 gives us 10.4 volts. So the terminal PD, the voltage that's actually sort of available to the 13 ohm resistor is this. And so now, if we really had our heart set on using this equation where we're plugging in sort of the voltage, that's the correct voltage that we need to use. There's 10.4 volts of terminal PD available to the 13 ohm resistor. So if we square that and then divide by our 13 ohm resistor, indeed, we get the same correct answer that we got when we calculated it using this equation. Knowing this equation spares you the trouble of having to calculate what the terminal PD is, because as soon as you know the current, you know that this is a valid equation to sort of calculate it. So different ways to think about it, but we have to sort of apply that thinking correctly. The correct answer here again is A.